Hi, physics. Mr. Janowski here. So this is homework 2, chapter 4, homework 2, problem 3. So what's going on here? So an astronaut on the moon drops a hammer from a height of 1.5 meters and observes that it takes 1.36 seconds to reach the ground. So part A, calculate the value for G on the moon. And there's our answer, but we don't know that yet. So we need to do step, So what are we looking for here? Calculate the value of G on the moon. So what we're looking for is little g, but not little g on Earth, not this number, little g on the moon, which should actually be capitalized there. My fault for missing that. Yeah, if you're talking about a moon of a planet, it should be lowercase. If you're talking about the moon of Earth, it should actually be capitalized. But anyhow, so g moon is equal to question mark, and what units will it have? It's an acceleration, so its units will be meters per second squared. On to step 1. So step 1 is make a sketch. So what do we have? We have the moon, which I will indicate by writing moon. So here is an astronaut standing on the moon. Boop. So it looks just like a regular person standing on Earth, but no, take my word for it, that's an astronaut standing on the moon in a spacesuit. And the astronaut is going to drop a hammer from a height of 1.5 meters. So here's a hammer. So the hammer is not moving at the beginning, but then the hammer is going to fall. And at the end, the hammer will be down here. Boop. So a very crooked looking hammer, because I'm not that great at using the Wacom tablet yet. Let me try to make it look a little more similar. Okay, so yeah, there's our hammer. Trust me, that's a hammer. So not moving at the beginning, but it is moving at the end, which means at the end it needs the speed lines to indicate that it's moving. So there's that. I'll add one more thing here. This is a height of 1.50 meters. So an optional step, but you know, it helps. So there we go. On to step 2. The variable bank. So this is a free fall problem. Things are going up and down, so we're using y's instead of x's. So y initial, y final, v initial, v final, a, and t. All right, so y initial is the height we're starting at, this one right here. So as always, just make that one 0. So 0 meters. Y final is the height we're ending at, so our height down here. This is 1.5 meters below y initial, and y initial is 0. So this needs to be minus 1.50 meters. The initial, how fast is the hammer moving at the beginning? Well, at the beginning, up here, there's no speed lines. So the astronaut has just dropped it. They didn't throw it up or down. So 0 meters per second. V final, how fast is the hammer moving at the end of the problem? Well, it's definitely moving because of the speed lines, but we don't know. So question mark, meters per second. A, what is accelerating this hammer? Well, it's going to be gravity, but it's not little g, the gravity on Earth. It's little g sub moon. The acceleration due to gravity on the moon, and that is equal to question mark, meters per second squared. That's actually what we're solving for. And t, how much time does it take for the hammer to go from here to here? We do know that. That is this number right here, 1.36 seconds. So I have a variable bank. I know 4 of the things, and I have 2 question marks. So that means this problem is solvable. If you know 4 things, you can solve it. So on to step 3, what are we looking for? We're looking for little g on the moon in meters per second squared. So actually, I'll do it over here this time to make a little more room. So this is what we're trying to solve for. Whoop. On to step 4, pick an equation. So the 2 conditions, it has to have the thing we're looking for. So this thing must have an a in it. So 1 has an a, 2 has an a, 3 has an a, 4 does not have an a. So it definitely won't be 4. And the other thing is we have to avoid any other question marks if there are any. And in this case, there is one. We don't know v final. So 1 avoids v final, so that's good. 2 has a v final. can't be 2. 3 has a v final, can't be 3. So it has to be equation 1. So I'm going to copy it down exactly. Delta y is equal to v initial t plus 1 half at squared. So there's my formula. Pro tip of the day, is there a useful 0? There is one. V initial is 0, which means V initial times t. Now the whole thing is going to be 0. So I get to lose that term and not worry about that, so that's good. So now delta y is equal to 1 half a t squared. On to the math. Step 5 is math. So I want to keep this problem in letters for as long as I can and just keep doing algebra to this thing until I have the thing I want by itself. And the thing I want is a. So the first thing I'm going to do is multiply both sides by 2 because I don't like this 1 half hanging out in front of the a. So when I do that, that'll give me 2 delta y on the left is equal to 2 times 1 half becomes a 1. So I don't need to worry about that. A t squared. Then I'm going to divide both sides by t squared to get rid of the t squared, or at least to get rid of it on the right. So dividing everything by t squared on the right, t squared over t squared, it just goes away. And that leaves me with, let me write over here to save a little bit of space, that leaves me with a is equal to, so I'm switching left and right here, 2 delta y over t squared. So I've done everything I can with the letters. Now I have to put in the numbers. So I get a is equal to 2 times delta y. So delta y is y final minus y initial. So minus 1.5 meters minus 0 meters, which is just minus 1.50 meters. And then this has to get divided by time squared. So time is this number right here. So 1.36 seconds squared. Now do this in your calculator carefully and make sure that you're doing 2 times minus 1.50 meters and then dividing by this number squared. Now if you get good with the calculator, you will be able to do this all in one shot. But let me actually take a little step here and show you this in 2 steps. If you're struggling with getting the order of operations you want into the calculator, there's no harm in slowing it down and doing it a little bit more deliberately. So 2 times minus 1.50 meters, that's going to give me minus 3.00 meters on the top. And then 1.36 squared. So on the bottom, that's going to give me 1.8496. And the units on the bottom at this point would actually be seconds squared, which seems weird, but don't worry about it. So then if you ask the calculator, what is 3 divided by 1.8496, the calculator will tell you that your answer is, I'm sorry, it should have been minus 3. So our answer will be minus 1.62 and then 1972318. But yeah, 3 sig figs is enough. So A is minus 1.62. And then our units, look, are going to be meters on the top divided by seconds squared. So meters per second squared, which is cool. This is what I wanted. So comparing this, doing our step, yeah, we were looking for g on the moon, which is a, the acceleration due to gravity on the moon. We wanted it in units of meters per second squared. That's what we got. We got a negative number. Well, that makes sense because even on the moon, gravity will pull things downwards. And is this a reasonable number for this? Which may be difficult to answer because none of you have been to the moon, and neither have I. So, yeah, we don't have a lot of direct experience with the moon. So how does this number compare to the only g that we're very familiar with, which is g is equal to minus 9.8 meters per second squared? I wish I hadn't crossed it out. I'm not going to erase it, I think. Yeah, cool. So it keeps the text. It just erases the crossing out that I did. Yeah, how does this number compare to it? It's in the same ballpark. It's smaller, but that kind of makes sense. We know that gravity is going to be a little bit weaker on the moon because the moon is smaller and less massive. So we do expect a number that's like this, but, a number that's like this one, but smaller. And that's what we got. So we're happy. So that's part A. Now for part B. Part B is a different kind of question, and I would not be surprised if many of you are very confused about this. This is just kind of a crazy curveball question that we haven't seen anything like. But part B, how does this compare to G on Earth? All right, so step for part B. How does this compare? What you really want is the ratio of little g on the moon divided by little g on the Earth. And what units do we expect this to have? Yeah, good question. Turns out this actually won't have units. And I'll show you why when we actually do this. So there's this. Yeah, you don't really need to do step one and all that thing. We don't need to make another sketch. All we're trying to do is compare these two things. So little g on the moon divided by little g on Earth. So this will be equal to something over something. The top something will be the value we just found for little g, minus 1.62 meters per second squared. And the bottom value is our regular value for little g on Earth, minus 9.8 meters per second squared. So if you ask your calculator, what is 1.62 or what is minus 1.62 divided by minus 9.8, and your calculator will tell you 0.1655. And how about the units? It's g divided by g, and both of those things are meters per second squared. So shouldn't this have units of meters per second squared? And it actually doesn't, because what happens is all of the units cancel when you do a ratio problem like this. So yeah, meters per second squared divided by meters per second squared. Well, the meters part just cancels, and the per second squared parts just cancel. So you end up with this. So this could be your final number, 0.1 0.1655. Yeah, so that's good enough. So that is, let me make this a little bit clearer. That is the ratio of G moon to G on the Earth. So this totally, that's a terrible box. This totally could be your final answer. But let me take it one step further and realize, let's see. If you take that number, how do I want to say this? If you just take 1 divided by 6, so I'm just kind of pulling that number out of the air because I happen to know it's the right answer. 1 divided by 6, and ask your calculator what that's equal to. Your calculator will tell you that has a decimal. It's 0.16, and then 6 repeating. So I just want to point out that the number we got for how little g on the moon compares to little g on Earth happens to be really close to the fraction 1 divided by 6. So just a little rule of thumb to remember, little g on the moon is about 1/6 the value of little g on Earth. It's not exactly it, but it's close. So kind of handy. And then finally on to part C. So how long would it take a hammer to fall 1.5 meters from rest on Earth? So this is actually just a regular kinematics problem. So start off as always with step How long would it take? We're looking for time. T equals question mark, and the units will be seconds. So our sketch. Step 1, here's our sketch. Whoop, terrible. Slightly better. So here's the ground, and let me just be clear. This is the ground on Earth. So now our astronaut is back on Earth, not being an astronaut anymore, just being a regular human being. And the astronaut is going to drop a hammer down to the surface. But this time the astronaut is doing it on Earth. This is still 1.50 meters. So again, from here on out, it's just a regular kinematics problem. So step 2, variable bank. Y initial, Y final, V initial, V final, A, and T. So Y initial height, always make that one 0. Y final, well, this is 1.5 meters lower than 0. So this is minus 1.50 meters. V initial, no speed lines. I forgot the speed lines. So there are speed lines here, but there are no speed lines up here. So that means V initial is 0 meters per second. The astronaut is just dropping it on Earth. V final, how fast is the hammer moving at the end of the problem? Well, it's definitely moving, but we don't know how fast. So question mark meters per second. A, what is accelerating this hammer? It's going to be little g, but remember, we're back on Earth. So we're at little g sub Earth. I mean, you don't really need to do that, obviously. And little g on Earth is minus 9.8 meters per second squared. And t, how much time does it take to get from here to here? We don't know this. This is what we're actually trying to solve for. So question mark seconds. Now we do our quick little step 3. The thing we're looking for is the time. And on to step 4. So we have to pick an equation. We need to pick an equation that has time in it. So 1 has time, 2 has time, 3 does not. Won't be 3. And 4 has time. The other condition is we have to avoid any other question marks. And the other question mark that we have this time is V final, which means we can use 1, we can't use 2, and we can't use 4 because 2 and 4 both have V finals in them. So the equation we're going to have is delta y is equal to V initial t plus 1/2 a t squared. We do have a useful 0 again. So V initial times t, that's going to be 0. This gives us delta y is equal to 1/2 a t squared. And the thing we're solving for here is t. So again, keep your problem in letters for as long as you can. Do all of the algebra to the letters. Just get the thing you want by itself on one side. The thing we want is t. So first things first, multiply everything by 2. That will give us 2 delta y on the left is equal to 2 times 1/2 is just 1. So this is equal to a t squared. Now I want to get rid of this a that's attached to my t squared. So I will divide both sides by a. So a goes away on the right side. And now we just have t squared on the right side with this stuff on the left side. So I want to take the square root of everything. And that's going to give me, and I'm switching left to right here, t is equal to, and again, this is a plus or minus kind of situation, plus or minus the square root of 2 delta y over a, which is really plus or minus the square root of, we have to put in the numbers, 2 times delta y is minus 1.50 meters divided by a, and remember a is little g on Earth, so this is divided by minus 9.8 meters per second squared. And if you do all of that in the calculator, what you'll end up with is t is equal to plus or minus 0.553 seconds. So that's 2 answers. Which one is it, the positive one or the negative one? The negative value of time would mean before we started the problem. So does the hammer hit the ground before the astronaut drops it? No, the hammer hits the ground after the astronaut drops it, which means it won't be the negative one. So I'll get rid of that. It will be the positive one. T is equal to, the plus is implied, 0.553 seconds. Now put a box around it to indicate that is your final answer. Grab your red pen and do step So did we solve for the right thing and give it the right units? Yes. We wanted t in units of seconds. That's what we got. 0.553 seconds. So that's about half a second. Does that make sense? If you held something 1.5 meters over the ground, so 4.5, 5 feet over the ground, and you let it go, does it make sense that it would take about half a second for that thing to reach the ground? So just imagine holding something, a meter stick and a half over the ground and letting it go. Would it take one misses and it's there? Yeah, that seems right. So we're happy with that answer. That is a sensible amount of time for this to take. So you give it a check. So hopefully that was helpful.